So many of you have heard this expression saying correlation does not imply causation. What does this mean exactly? We'll try to explain in this video. So first, let's think about what we know about correlation and dependence. So we know that if x and y are independent, then the covariance and the correlation of x and y are zero. And if the correlation of x and y is not zero, then x and y are dependent. But there is no implication in the opposite directions. So you can have that the covariance is zero, but the variables are dependent. So if x is a random variable that takes n discrete values and y is a random variable that takes m discrete values, then checking for independence requires checking n times m values, right? We basically have to look at the table where it has all of the joint probabilities. Checking for zero correlation requires calculation of just one value, so that's much easier. Correlation basically is the quick and dirty way to detect strong dependencies, but it might not be able to find dependencies that are not linear. Okay, so correlation versus dependence, you have non-zero correlation implies dependence, and dependence does not imply correlation. Now let's think about causality. Causality is what we really would like to understand when we study phenomena in nature or in medicine. So we know that correlation implies dependence. Dependence does not necessarily imply correlation, but how does this relate to causality? Correlation is not directional, but causation is. Causation is something happens at one point which causes something at a later point. So a simple example, the density of mosquitoes is correlated with the occurrence of malaria. We can conclude that mosquitoes cause malaria, which is true. But we can also conclude that malaria causes more mosquitoes, which is false. So the correlation doesn't tell us which causes the other. So let's think about conditioning. Maybe with independence and dependence, we can do that. Causation is directional. Mosquitoes cause malaria, but malaria does not cause mosquitoes. But correlation is non-directional. And conditioning seems directional, but this is superficial. So basically, if PA given B is not equal to PA times PB, then both PA given B is not equal to PA, and PB given A is not equal to BB. So it's really not directional in the sense that we want, right? So basically, whenever you have dependence, you have the conditional being unequal in both directions. Okay, so let's think some more about what is the difference between correlation and causation. There's various things that can come in the way from between deciding whether something is whether correlation implies causation or not. Okay, so here's an example. The more firemen are fighting the fire, the bigger the fire. Therefore, firemen cause an increase in the size of fire. Right? Bigger fire, there's more firemen. So the causation here is reversed, right? So basically, we are seeing that there are more people, there are more firemen fighting the fire, the bigger fire. That means that the firemen, the more firemen you have, the bigger the fire, and so firemen are really causing fires, and the best thing to do is not to send any firemen, right? So that is obviously an incorrect direction. Let's think about a different one. So suppose that Jack complains that if he goes to sleep with shoes on, he wakes up with a headache. Does this mean that sleeping with shoes causes his headaches? Not necessarily, because they might be both the result of drinking too much the night before, right? So drinking too much causes a morning headache, and because he drank so much, he didn't take the shoes off before he went to sleep. Okay, so that is not a causation either. So it's determining causation can be very hard, and usually it requires that we intervene. So we somehow change the situation in order to see what causes what. So how can you determine whether or not the sleeping shoes cause headaches? Here are several options. Stop drinking, flip a coin to decide whether to wear shoes to bed, flip a coin to decide whether or not to drink, or observe that every time you drank, you both slept with shoes and got up with a headache. Okay, so the flipping of a coin is basically probably a good approach because it changes what happens, and then we can see what the correlation is. Okay. So here is another example more from real life. Suppose that we want to know whether a store brand medicine is worse than a name brand medicine. Suppose we have access to both medical records and to drugstore records. We observe a correlation between consuming generic brand and the time until the patient gets well. In other words, the time to heal increases when taking generic brands relative to the name brand. Can we conclude then that the name brand is better? Well, not really necessarily, because here is an alternative explanation. Name brands are more expensive, therefore more wealthy people buy them, and more wealthy people tend to be more healthy and heal more quickly. So it's really just something that is a result of a separate cause, which is the affordability of the different brands. So we need to control for external variables such as wealth. Clinical trials are an important way in which we want to really see causation. Okay, so developing a drug takes 10-15 years and hundreds of millions of dollars. And after testing on animal, the final stage is a clinical trial, a test on human patients. It's very expensive. So even very big, rich companies cannot afford to have the experiment done on more than a few hundred patients. And the important thing is they need to demonstrate causality. So they need to show that taking the medication causes an improvement in the patient's health and is not just correlated with it. So this requires a controlled study. On the other hand, nowadays we have more and more the ability to do observational studies. So we have access to medical records. It is becoming possible to measure effectiveness of drug on millions of people as compared to a few hundreds in controlled studies. So the potential is for revolutionizing medical research. The challenge is that it's hard to control for the non-causal correlations. Challenge can be met by controlling potential causes, wealth, age, race, so we can do a more sophisticated data